In VLSI technology course, so far we have discussed on the topics like contamination, clean room, wafer cleaning process, and then we discussed on oxidation of silicon, then lithography, and lastly we discussed on impurity diffusion in semiconductors. So today we will start another chapter, that is ion implantation. It is a very important and useful topic for VLSI fabrication process. And so far we have seen in a diffusion process we incorporate dopants, and dopant atoms are diffused at a temperature, and that temperature is in the range of 800 to 1200 degrees centigrade. Considering that high temperature process, there is a problem, and that problem, hopefully you are aware that high temperature process redistributes impurities. That means the impurity layer, diffuse layer, which were done at the early stages, they will redistribute and they will occupy larger space laterally and vertically also. So always a low temperature process in VLSI is advantageous. In that respect, ion implantation is always in a good position. Another point we have seen that in a diffusion process, the control of impurity atoms is not that much accurate, which we need in case of present VLSI process technology. At the same time, the maximum amount of dopant, that was also limited by the solid solubility limit, and you cannot increase the dopant level more than solid solubility limit. That was also one of the disadvantage of diffusion process. Now, ion implantation is a technique by which you can incorporate dopants in a highly controlled manner. At the same time, the reliability is extremely good. That means batch to batch implantation with same parameters, you will get the conductivity chain in the semiconductor is exactly same. That is reliability. So that is very good in case of ion implantation. And this particular technique was first given by Skal from Bell Lab in 1954, and that's why the ion implantation technique is patented by Skal. But that time it was not commercially used. The commercial application of ion implantation process in integrated circuit fabrication was incorporated sometimes in 1960s, and later on in 1968 Gibbons summarized all the processes and techniques involved in ion implantation process for incorporation of impurity diffusion. And after that, this particular technique is highly accepted in VLSI process, and every year the progress in R&D on this particular topic was discussed in international conferences, and those international conference documents are very important to understand the progress of implantation research and implantation research. And the ion implantation, like diffusion, the parameters are not thermodynamic. That means in diffusion process we use temperature and time as the diffusion parameter, but in ion implantation they are all electrical. That is ion current, dose and energy. Those are the implantation parameters. Ion implantation technique has a lot of applications in VLSI, and that is in MOS or say CMOS technology, starting from threshold adjustment, source drain implantation, and at present in most of the VLSI processes people prefer ion implantation rather than diffusion. Not only in device fabrication, this is device fabrication like surface implantation, threshold adjustment, and source drain or emitter or base or collector or BJT fabrication. The ion implantation technique is highly used for buried insulated. That means if you want to have an insulated layer inside the bulk of the semiconductor crystal, that is also possible by this technique, and we'll discuss that part also. And rather than this buried insulation and device active components of devices, buried implantation is also used nowadays in shallow junction formation. And this shallow junction means the junction depth is of the order of few tens of angstrom. Okay, junction depth can be varied in ion implantation by changing the energy of implantation, and that energy of implantation can be varied from few kilo electron volt to few megavolt, low energy to very high energy. And doses of implantation can be changed from 10 to the power 12 atom per centimeter square to 10 to the power 18 atoms per centimeter square. 10 to the power 12 dose is normally used for threshold adjustment, and a higher side 10 to the power 18 dose is used for the buried insulator application. Okay, and nowadays the ion beam technique or these ion implantation techniques is used for focused ion beam process, and the focused ion beam process enables you to write dopant pattern on silicon without any mask. That is most advanced technique of getting dopant pattern in a control and reliability and high reliability, and this is used for shallow devices nowadays. And there are two classes of ion implantation process. One is low energy low dose, and another is high energy high dose. Low energy low dose on extreme side, that is used for shallow junction formation, and high energy high dose, those dose levels and energies are used for buried insulator applications, and medium energies are used for fabrication of VLSI devices, that is BJTs or MOSFETs. And if you look into the literature, you will find last 5 years more than 3,000 papers have been published on ion implantation, and even still lot of scope is there for further research of ion implantation in silicon. And in this particular chapter we will discuss one by one the theory of ion implantation and the implantation techniques, ion implantation machines, and its various application in VLSI. So now we will just first discuss on the specific features of ion implantation. Ion implantation is a process of introduction of ionized projectile atoms, and those ionized projectile atoms are impurity, into targets, and those targets we assume here is silicon substrate, with enough energy to penetrate beyond surface region of a single crystal substrate in order to change its electronic properties. That is ion implantation process. That means what you have to do, dopant atoms are first vaporized and then they are ionized, and those ions are accelerated with the help of electric or magnetic field, and those accelerated ions are bombarded or those ions bombard directly on silicon substrate. These dopant atoms, after bombardment on the surface of the silicon single crystal surface, they damage the crystal lattice, they colloid with silicon atoms, and inside the bulk single crystal silicon, they gradually lose their energy, and finally they come to rest at some depth within the crystal lattice. That is the complete phenomena in ion implantation process. That means first you have to choose the dopant. They have to vaporize so that you can get the dopant atoms, and then they are ionized, and those ions are accelerated and bombarded on the silicon surface. Okay, that is in a nutshell the total ion implantation process. Now, specific features of ion implantation. Why ion implantation is very much popular in present VLSI process? Those are mentioned in this view graph. You can see one of the main feature of ion implantation technique is precise control over the number of implanted dopants. Control of impurity in ion implantation is of the order of plus minus 1% over the range of doses. Normally used doses are 10 to the power 11 to 10 to the power 17 ions per centimeter square, and there you can see the ion implantation control is plus minus, that means impurity control is plus minus 1%. But in case of diffusion, this value means this impurity control is at the best 5 to 10% at high concentrations, and this value is still worse at low concentration level. That means precise control over number of implanted dopants are achieved in ion implantation process of the order of plus minus 1% only. Next point to be remembered is the low temperature process, and here temperature is within 400 degrees centigrade during implantation. That means you are not heating the substrate. As the ions are accelerated and they bombard on the silicon surface, locally the temperature will increase, and that temperature will not exceed beyond 400 degrees centigrade. It's a really very low temperature, and at that temperature inside the silicon the doped layer will not expand or redistribute. That is one of the big advantage in ion implantation. And wide variety of profiles can be obtained by controlling energy and dose. What do you mean by that? You have seen in diffusion profile, you got either error function diffusion profile or Gaussian diffusion profile. But in ion implantation process, you can make arbitrary doping profile. That means you can make doping profile in graded or in various step doping profile. You can get it because you can have multiple implantation, and in this multiple implantation you can vary energy and doses gradually. That means first you implant, for example, say 100 keV and dose is say 10 to the power 15. So 100 keV means those impurity atoms will go deeper into the silicon. Then you implant in the same impurity atom with a dose of say 50 keV and energy of 50 keV and same dose maybe. Then you go for 25 keV, then you can go for 10 keV. In this way, if you continuously change the energy at the same dose, that means the profile that means depth of penetration will be different, but level will be the same. So, or at the same time you can change both energy and dose, so that the peak concentration and the level of penetration both will also change. So, in this way you can adjust the doping profile at your wish by multiple implantation techniques of different energy and dose values. Now, another point is that important point is ion implantation is a non-equilibrium process. What do you mean by that? That is, you can introduce impurity in excess of solid solubility. That just now I mentioned at the beginning. In diffusion, you cannot increase the solid solubility limit in order to have a repeatable diffusion process. Okay. More than solid solubility limit of the dopant atoms you can implant into silicon. Implantation is conducted in vacuum. So, if you conduct a process in vacuum, that particular process will be highly clean and is a dry process. Because if you do the process in ambient environment or at reasonable gas pressure, that means in nitrogen or in other neutral gas ambient, so there is a chance of contamination from the gas and from the environment. But implantation is done in vacuum, and this vacuum is very high, of the order of 10 to the power -7 or -8 torr. So, in that vacuum you can get a clean environment and process is dry. So, the undesired incorporation of impurity atom into the silicon will not be there in ion implantation technique. The implantation energy rises from 1 keV to 1 mega electron volt, resulting in ion distribution with average depths ranging from few tenths of angstrom to few thousandths of angstrom, that is from 100 angstrom to 10 micron, because the depth is proportional to ion energy. Doses of implantation range from 10 to the power 12 ions per centimeter square to 10 to the power 18 ions per centimeter square, and these doses can be controlled by monitoring the ion current during implantation. Beam current, this is another parameter. That means the beam current is dependent on how many ions per unit area incident on the silicon surface. If the number of ions terminated on the silicon surface is more, then automatically beam current will be more. Okay. So, those can be controlled by monitoring the ion beam current. This ion implantation technique is highly sophisticated and expensive technique. Why it is expensive? The equipment is extremely expensive because you need lot of controlling parameters. For example, high energy, acceleration you have to give to the ions. So, for that, those electrodes, that is one part, and another part is ion generation of ion beams, one part, and lastly the whole thing is conducted in a high vacuum, that is another additional cost. So, the total implantation equipment is extremely expensive one. At the same time, ion implantation you cannot have batch fabrication. The implantation is done individual wafers one by one. So, you know that if a wafer is implanted individually, it will take longer time and throughput will be not that high, so it will be expensive. The major concern in ion implantation process is the damage. Ion implantation results in damage to the semiconductor, and the damages can be removed by annealing at elevated temperature. Thus, always ion implantation is followed by annealing at a high temperature, and this annealing heals some or all of the damages. What happens just after implantation? The surface of the silicon is completely damaged, and it will become amorphous in nature. It will not be single crystal. Just after implantation, if you want to measure the seat resistance or resistivity, and you will find that resistivity is extremely high, because the single crystal nature of the silicon is lost just after implantation. And in order to remove damage, in order to have again the recrystallization of the silicon material from amorphous nature to crystal nature, then you have to go for annealing. And after annealing, you will see the amorphous nature has gone, and again the single crystal nature of the silicon is regained. So there you can easily measure the seat resistance. That's why just after ion implantation, you don't try to measure the resistivity or seat resistance of that particular layer. After annealing, you will have the value of the seat resistance, and there you have to study how much annealing temperature you have to give, so that you will get the repeatable value of the seat resistance. That means the annealing time and annealing temperature is decided by the need of recrystallization of the silicon. That means from amorphous to recrystallization, that is some sort of solid phase epitaxy, you can say. Okay. So that means by implantation you can amorphize a layer. That is also another application of ion implantation, amorphization, and then healing the damages, and you will get the complete single crystal layer after the high temperature annealing. So in a present VLSI process, the pre-deposition diffusion is totally replaced by ion implantation technique. The question is why? To answer that question, we can mention few points, and those points are control of doping profile, shallow junction formation, maximum doping level, control parameter, electrical conductivity, and damages. And this particular table shows the implantation and pre-deposition diffusion comparison. So far as control of doping profile is concerned, we mentioned that implantation is excellent and pre-deposition diffusion is good. Shallow junction formation you cannot make using pre-deposition diffusion, but in implantation technique you can make minimum 1000 angstrom of junction depth. Even nowadays people have reported they are able to make junctions less than 1000 angstrom. Nearly 50-60 angstrom junction depth have been reported. Maximum doping level in implantation, always it is greater than solid solubility, you can make if you want, but in pre-deposition diffusion the maximum doping is limited by solid solubility limit of the dopants at that particular temperature. Now control parameters in implantation, it is electrical, that is ion energy, dose, ion current, etc. But control parameter in pre-deposition is thermodynamic in nature, that is temperature and time. Electrical conductivity, just after implantation electrical conductivity is very poor, and for getting good electrical conductivity it requires annealing. But electrical conductivity in pre-deposition diffusion is very good. Just after pre-deposition you can measure the conductivity of the particular layer. Damages in implantation is high compared to pre-deposition diffusion. Their damage is low, but although damages is high, there are certain techniques so that you can improve the quality of the crystal again. That technique is proper annealing sequence. Okay. Now, effects of ions and atoms bombarding the surface of a solid. That means you are bombarding high energy ion on silicon surface. And in the earlier class, I have explained the ion beam etching or sputtering. There also high energy ion beams are bombarded on silicon surface. That means when the sputtering will take place, when an implantation will take place. In both cases, you are bombarding the silicon surface with ion beams. Okay. Now that is discussed here. The physical sputtering or milling will take place when the energy is less than 10 keV nearly. When the energy of the ions or atoms which are bombarding on the surface of the silicon is less than 10 keV, then physical sputtering or milling will take place. And at the same time, when the energy is within that limit, ion induced chemical reaction or etching will take place for low energies, and those etching techniques are RIE, reactive ion etching, or RIB, reactive ion beam etching. Those part I have already discussed in dry etching process. But when the energy is more than 10 keV, then ion implantation takes place. For implantation, normally the ion implantation, the energy of the impurity atoms are more than 10 keV. Now, this particular curve shows ion energy versus sputter yield. And here you can see that if the ion energy is extremely low, then sputtered yield is poor. At a certain amount of energy, if you increase, then the sputtered yield is maximum. And again, very high energy, you can see from the curve, the sputtered yield reduces. Why? Because if you increase the energy of the ion more than this limit, so then instead of sputtering, then what is happening? That is implantation. Sputtering means what you are doing? Surface silicon atoms are taken out. That is etching, isn't it? But in implantation, you are not removing the single crystal silicon from the surface. You are rather incorporating the dopant atom deep into the silicon. That means if the energy is very low, then also sputtered yield is low, and energy is very high, which is of the order more than 10 keV, then also sputtered yield is low. Gradually it reduces because of implantation. Okay. Now, what are the ions normally used for implantation, for doping of semiconductor material? And in our discussion on the ion implantation technique, we consider only silicon substrate. Other substrates are rarely used in VLSI process. That's why we will confine our discussion on silicon only. So now ions for semiconductor dopings are boron and BF2. Okay, BF2 is the fluoride of borons. So BF2 implantation is also done. Boron and BF2 for p-type in silicon, zinc plus zinc ion or cadmium for p-type in gallium arsenide. These are the commonly used doping ions for silicon and gallium arsenide. Phosphorus, arsenic, antimony for n-type in silicon. Sulfur and silicon are used as an n-type dopant in gallium arsenide. Typical energy used for doping in silicon or gallium arsenide lies in the range of 10 keV to 500 keV. Typical ion current is in the range of 10 microampere to 10 milliampere. typical dose is in the range of 10 to the power 11 to 12 to 10 to the power 16 ions per centimeter square. So these are the energy, dose, ion current, and the dopant atoms information for ion implantation. Now we'll discuss on range and straggle of implanted ions. So what happens after ions bombard on silicon surface? Those ions, means those ionized particles, moving through solid silicon, they will lose energy either via collision between the ions and nuclei of the substrate, or by interaction between the ion and electron in the solid. That means when the ions are implanted, then inside the crystal they undergo lot of collisions, and those collisions will take place with ions, nuclei of the ions, and the target atom, and those target atom here are silicon atoms. So one collision is between the nuclei of silicon and nuclei of the ion atom, and during these collisions some of the energy will be lost, and the second interaction is between the ions and the electrons, orbital electrons of target atom, that is silicon. There are two interactions. One is repulsive in nature, that is between nuclei of the dopant ions and the target atom, and the other one is the orbital electrons of the target, that means silicon, and the ions, that is implanted species. So these two interactions will take place, and because of these interactions the energy will gradually decay. The ions will lose their energies, and ultimately after some depth it will stop. Ions are not moving inside the crystal over a longer time, so the energy is lost and become the ions will be at zero velocity at some time, and it will be at rest. Okay, so this distance, average distance a ion travel inside the crystal, is known as the range. That's why it is known as range of implanted ions. And straggle is another parameter that we will discuss now. Now in this diagram you can see a semiconductor material. By these green lines it is shown. Ions bombard at the surface, and that particular ion proceed inside the crystal through lot of collisions, and say after traveling an average distance r, the ions lose its energy completely and it will be at rest. That is the average distance from this point to this point. Some ions may travel without collision directly in a straight line path, but those ions are very few in number. Okay, most of the ions, more ions, will undergo collisions, and so their path will not be exactly straight line in nature. They will follow any zigzag path, and after losing its energy completely it will come to rest. So that is average distance is known as range, and it is written as r. And another term is given as rp. Projection of r is known as rp, that is projected range. Projection of r is known as rp. And another parameter is also important in ion implantation technique, that is shown here, delta rp and delta are perpendicular. That is what this RP value is not fixed. That means in this perpendicular direction there is a width, you can say. That means that can vary. Some RP may end up here, some RP may end up there. So that means there is a range of RP. Okay, and that deviation of RP is known as delta RP. That is perpendicular direction is delta RP, and another in a perpendicular to the incidence direction is delta R perpendicular. Okay, that means there is a variation of termination of this R in this direction also, that is delta R perpendicular, and the horizontal direction, that means this direction, is delta RP. Now, what are the definition of those points? Range is defined as the average distance traveled by an implanted ion while coming to rest in the solid. That is the definition of range. Now coming projected range, that is RP. Projected range is the projection of the range R in the direction of incidence. It is the projection of the range R in the direction of incidence. Then is fluctuation or standard deviation. Fluctuation or standard deviation is a measure of the spread of distribution expressed in delta RP that I have shown in the earlier diagram. That spread, fluctuation and spread may be in the direction of incidence, maybe in the perpendicular to the direction of incidence. That's why two values are shown in earlier diagram. One is delta RP and another is delta R perpendicular. That means this deviation or fluctuation or spread is delta RP. One is in the incidence direction, other is normal to the incidence direction. Okay. Now next is the ion stopping mechanism. How the ion stops? Just now I mentioned there are two mechanisms. One is known as nuclear stopping mechanism and other is known as electronic stopping mechanism. And nuclear stopping mechanism is that mechanism where repulsion scattering due to electrostatic forces between the nuclei takes place. Repulsion scattering, nuclei of the ion and the nuclei of the target material, that is silicon here, projectile ion nuclei and the target nuclei, that is silicon, they will scatter because of repulsive force and they loses most of their energy as a result of strongly inelastic scattering process. Ions cannot penetrate much into the substrate and are stopped at very shallow depths. That is known as nuclear stopping mechanism. The next one is the electronic stopping mechanism. What is that? Scattering due to electrostatic interaction between the orbital electrons of the incident ion and those of the lattice atom. That is electronic stopping. Orbital electrons of the incident ion and those of the lattice atom, they interact with each other. This interaction is obviously a weaker interaction compared to nuclear stopping, because mass of these electrons are less compared to the nuclei. In the doses, this is very weaker interaction, and doses not lead to much energy and does not lead to much energy loss. Electron stopping mechanism does not lead to much energy loss because it is a weaker interaction. Okay. Now, ion scattering and stopping mechanism, how it takes place. The lattice binding energy of single crystal silicon is of the order of 10 to 20 electron volt. Now, when a ion of energy more than the binding energy is incident on the surface of the silicon, then it exceeds the binding energy and the amorphization takes place. The implantation energy is of the order of 50 keV or say 40 keV, in that range in normal cases. So that is very high compared to the lattice binding energy, which is in the range of 10 to 20 electron volt only. So this close encounter and interaction with the nuclei, which is known as nuclear stopping, so that is taking place, and that helps to stop the ions. Ion can lose energy to orbital electrons, that is known as electronic stopping. The stopping power is another term, and this stopping power is defined as the energy loss per unit length, and it is known as S. Stopping power means the energy loss per unit path length. Energy loss of what? Energy loss of the ion which is implanted into the silicon. Energy loss per unit path length S, that is given by d dx nuclear plus d dx electronic. First one is because of nuclear and the second one is because of electronic. So that is the stopping power S. Okay. Now, the ion stopping is shown in this diagram, how it stops. This is one simulation result, and that simulation result is a Monte Carlo calculation, Monte Carlo method. Because here all the collisions does not follow a regular path. This is the surface of the crystal, and the ions are incident at this surface, and they will penetrate. And this collision or the scattering, you can say, scattering does not follow a regular path. This is a arbitrary path. Statistical distribution of the whole process will take place, and that statistical distribution of the trajectories means path of ions inside the crystal, they can be obtained by Monte Carlo simulation, Monte Carlo calculation. And now you can see the ions are penetrating. Some of the ions are lost at a shallower depth. Some of the ions traverse a longer distance into the crystal. Why? Because all the atoms will not experience same number of scattering or same number of collision, because some of the atoms may choose a path in between the host crystal atoms, because you have seen the diamond crystal structure. In the lattice point, silicon atoms are there. In between lattice point, the lattice distance, the gap. Through that gap, if a particular atom is fortunate enough that it will follow that path, so you will travel in this particular channel without any collision, and they can end up at a larger distance. They can travel at a larger distance inside the single crystal silicon. But the unfortunate guy who will incident on the surface at a particular grazing angle, they will face lot of host crystal atoms, and lot of nuclear scattering will take place, and they will stop immediately within few angstrom maybe. So that's why this the statistical distribution of the trajectories in various direction. It may be in the vertical direction, it may be in the lateral directions. That is the ion stopping mechanism. Softwares are available to calculate the trajectories using Monte Carlo software package, Monte Carlo distribution. Okay. So this is regarding ion stopping. And if you see the ion stopping power as a function of ion velocity, then the profile is like this. There are three regions. One is low energy region, intermediate energy region, and high energy region. The region 1, that is in the range of 10 to 100 keV range, most of the ion implantation process is in this region. 100 within 100 keV. And intermediate region is only electronic stopping. And at very high energy, this is known as Bethe block region. That is not common in the semiconductor process implantation. But most common implantations are in the region 1, which is low energy region. There the major stopping mechanism is nuclear stopping. That curve is also shown. And the little bit higher electronic stopping, and mostly the nuclear stopping. Okay, this is the region which is the normal ion stopping in normal implantation, use the nuclear and electron energy. So with this profile, let me stop today. Next one is the profile calculation, and those particular topics I will cover in the next lecture.